तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. So in our series of lectures on basic electronics, learning by doing, we will move on to the next. Before we do that, as usual we will recapitulate what we discussed in the previous lecture. You might recall, as you see on the screen, we discussed about the basic concept of negative feedback in amplifiers and how there could be 4 different types of negative feedback circuits that we can get depending upon what we sense at the output and what we give at the input. For example, you can sense a voltage and give it as a voltage at the input, or you can sense voltage and give it as a feedback current at the input stage, etc. So 4 different types of negative feedback can be constructed, and these 4 different types of circuits will lead to 4 different characteristics depending on the output and input impedances. We discussed all these 4 types of negative feedback, and then we took one typical example of one of the feedback circuit, which is a non-inverting voltage amplifier, where the output voltage is sensed and given as voltage in series with the input, and therefore the effect of that, as you might recall, is to increase the input impedance and decrease the output impedance so that it becomes much closer to an ideal voltage amplifier. An ideal voltage amplifier should have infinite resistance at the input and it should have 0 resistance at the output so that it can drive different type of loads. It is also called voltage series feedback or voltage controlled voltage source circuit. So this is what we discussed in the previous lecture. Now in the present lecture we will move on to the next type of a feedback circuit. You can see on the screen 4 different types of feedback circuits again are shown for clarity. You might recall we have done that in the last lecture also, where voltage is sensed and given as voltage at the input, voltage sensed and given as voltage in the shunt form, currents sensed in series at the output and given as voltage at the input, and current is sensed and given as a shunt at the input. These are the 4 different circuits, and now what we are going to see is the second type, where we sense voltage at the output in parallel, and at the input also we give it in shunt in parallel. So this is the feedback that we are going to discuss now. You know what is the effect of that on the input and output resistance of your amplifier. This block at the center is the amplifier. So you can see what is going to happen. If you look from the output side, the output resistance, Thevenin's resistance of the amplifier and the output resistance of the feedback network, they will come in parallel. From when I look from here, this and this will come in parallel, and when 2 resistors are in parallel, you know what is the effect of that. The effect of that is to reduce the effective resistance, and therefore the effect of this feedback arrangement on the output resistance is to decrease the resistance. So that is what is shown here. Voltage sensed in parallel or output effective is parallel value of R output and RF output, where F output is the resistance of the feedback network, Thevenin's resistance as seen from the output side. So R out effective will be less than the previous RO without feedback. So that is a consequence of this feedback. And if you look at the input, you find this is also connected in shunt, that means in parallel. So if I look from here, the effect of that you would have immediately guessed is also to reduce the resistance, effective resistance, because voltage fed back in parallel, or effective is parallel value of REI, which is the Thevenin's equivalent resistance of your amplifier, and RIF or RFI, which is the feedback input resistance of the feedback network. So they are coming in parallel, so that the input resistance also is effectively reduced. So both the input resistance is reduced and the output resistance is reduced. The effect of output resistance being reduced is to make sure that the output becomes much closer to an voltage source. So it becomes an voltage output and it is a voltage source reasonably. The input side, the resistance increases, means the input is not a voltage drive, but it is a current drive. Only when the current drive is connected to a very small resistance, the current cannot change significantly in the circuit, and therefore it will be very useful to introduce a current at the input side. So what you have at the input is a current, because the input resistance is very small, and what you get at the output is a voltage, because the output resistance is very small. So that is why it is called current controlled. The input current is controlling the voltage at the output, and therefore current controlled voltage source. So having looked at it, we will actually look at one of the typical circuit, using an op amp. So the circuit is very simple, as you can see. All that we have done is just connected the output high point to the input high point through a resistor R2, which is the feedback network. So the feedback network is a one single resistor, and the entire voltage is connected here. Therefore you can immediately imagine that the feedback ratio, the fraction beta, is 1 in this case, because the entire voltage is given at the input. So this actually is effectively a trans resistance amplifier, because the relationship between the output and the input is a relationship between V out and I in, and the dimensions of V out and I in is resistance, and therefore this is called a trans resistance amplifier. It is also called current controlled voltage source, because the input current is the one which is producing the voltage output, and it is also called current to voltage converter. So if I have some sensor or something which produces a current, the best method I could use is I will connect that current to this type of a circuit, so that the output becomes a voltage. The current is converted into voltage. Effectively the amplifier acts as a ideal resistance. Now how do we get that relationship? The exact relationship is as shown on the figure here. V output is equal to minus I input R2 multiplied by AOL by 1 plus AOL. The beta factor is missing here, because beta is 1 and therefore it is not there, but AOL is a very large quantity, open loop gain, about 10 power 5 in the case of op amp, 741. Therefore this ratio is going to be almost 1, and therefore V output is equal to minus I in into R2. So that is the relationship. V in is equal to minus. Why there is a minus? The minus sign shows that there is a phase inversion. The output voltage is negative. The input current is a source. You provide a current source, then you get a negative voltage. If you provide a current sink at the input, you will get a plus voltage. So there is a phase inversion at the output because of this, and R2 is the feedback resistance in this circuit. You would not have understood how I obtained the relationship directly. Therefore it may be much easier to look at it in a slightly different way. The same circuit can be understood in a much simpler way. For that we have to realize that what is the concept of virtual earth or virtual ground at the inverting input. So we will try to understand the concept of the virtual ground. Now to understand that, we should understand the transfer characteristics of an op amp. So this graph that you see on the screen is a typical transfer characteristics of an op amp like a 741. What do you see here? On the x axis you have voltage input, on to the right it is plus V in, on to the left it is minus V in. Similarly the y coordinate is corresponding to the output voltage, and above you have the plus V output and below you have the minus V output from the origin. So if I have these, if I now take an op amp, typical op amp, start applying voltage from very large negative values, keep on decreasing the input voltage from minus 10 volts, 15 volts, and then keep on going till it becomes plus 10 volts input. What will be the output for an op amp? That is what we should worry about. That is what the transfer characteristics is. And you can see the yellow line shown here is corresponding to the behavior of the op amp. I will explain to you why, how. So now what is happening? If I give different voltages at the input, negative voltages, you would find the output will become minus VCC, minus 15 volts for all the negative voltages beyond some limit threshold. Similarly, on the plus side, beyond certain threshold, whatever positive voltage I give will result in the plus VCC 15 volts. Because you have the open loop gain, this is without feedback, the open loop gain here is 10 to the power of 5. So if whatever voltage you give, if I multiply by 10 power of 5, if it comes larger than the power supply voltage with which you have energized your circuit, then the output will saturate at plus 15 volts, because no amplifier can amplify more than the power supply voltage that you have supplied. So here the power supply voltage is plus 15 and minus 15. So the maximum voltage which will show a normal amplifier behavior is given by 15 volts divided by 10 power 5 volts at the input. That is what I have shown in the next thing. What is the maximum input voltage that can be connected between the two terminals of an op amp? On the plus side, that will be equal to, you can at the maximum get 15 volts, divide by the open loop gain, that will give you the maximum voltage. In a typical case where we have taken the illustration, plus 15 volts is the power supply voltage and 10 power 5 is the open loop gain. Therefore you can see 15 by 10 power 5, or I add 2 zeros on both numerator and denominator, it can become 150 microvolt. So the maximum input voltage up to which the amplifier will behave as a linear amplifier with a linear output input relationship is 150 microvolts on the plus side. In a similar way, you can identify the corresponding minimum voltage on the negative side is also minus 150 microvolt. So the two inputs of an op amp cannot be different from each other by more than plus or minus 150 microvolt. This is a very important concept which will help you to understand many of the principles of working of the circuit. So at any time when an amplifier is constructed using op amp, the two inputs cannot be differing from each other by more than plus or minus 150 microvolt. 150 microvolt is such a very small value, so that in principle you can use it as a thumb rule that in any amplifier using op amps, the two inputs should be almost at the same voltage level. So this is a very important concept which will help us to understand many of the things. That is what is shown here. So this V plus on the input side and the V minus on the input side, they are about 150 microvolts on either side, and only between them you find there is a straight line, and the slope of the straight line is nothing but the open loop gain. In this case typically it is 10 power 5. So beyond that 150 microvolts, the output saturates at plus 15 volts. Whatever input voltage you apply, it cannot be multiplied by that 10 power 5, because if you multiply by 10 power 5 you get a much larger number, and such high voltages cannot be generated because the applied voltage itself is plus 15. Therefore it will saturate at plus 15. Similarly on the negative side, minus 15. So with this concept in background, we can get the two important concepts with reference to understanding the operational amplifier circuits. They are, the two input voltages will almost be equal to each other within plus or minus approximately 150 microvolt. The second important point is no current will flow into the input terminal ideally. This is because in general the operational amplifier input resistance is very large, and therefore the no current should, there should be a finite current, because it will be, you can imagine the input stage we have already discussed is nothing but a difference amplifier, differential amplifier, and therefore the basis of the two transistors which perform the long tail pair will be the input stage of any op amp. Therefore, there should be a finite base current for an amplifier to work, differential amplifier to work. Even though it is a finite current, we know that finite current is very, very small because it is a base current, and therefore in all practical purposes we can assume that to be too small compared to the normal currents that we will be handling in such amplifiers, and therefore it is reasonably safe to say no current will flow into the input terminal, even though we remember that there will be a very, very small finite current which is called the input bias current, which is required to be sent into the base of the two differential amplifier. Now, having understood this concept, let us look at the circuit once more here. This is the same circuit which is called the current to voltage converter. Now, we wanted to understand how the output is given by minus I1 I in into RF or R2 whatever. Now, you can see one of the input terminal V2 is connected to ground. If this is connected to ground, then without looking at the amplifier you can say this corresponding other input V1 should also be very close to ground within plus or minus 150 microvolts. So, V1 cannot be different from V2 within beyond 150 microvolts on either side. So, therefore, if this is ground for all practical purposes, this also can be taken to be very close to ground or almost ground. So, you find this point is not directly connected to the ground, but still it is very close to the ground voltage as long as this terminal is connected to ground, the V2. Therefore, this point is virtually at ground potential, and that is why this point is called virtual ground. You know, virtual images in mirrors and lenses, the image which cannot be caught on a screen is called virtual. It looks almost real, the image that you see in a mirror, but then it is virtual. You know that you are not standing behind the wall where the image is formed, and the same way, even though it is very close to the ground potential, it is not directly connected to ground potential. This is ground potential close to ground potential because the other terminal is at ground potential. Therefore, this becomes a virtual ground or virtual earth point. So, if you realize that, many of the understanding of operational amplifier circuits becomes rather simple. Now, I am now sending a current into this virtual ground point, and because there could be any current, there could not be any current through the op amp, that is also we have seen the bias current is going to be very, very small. Therefore, the entire current which comes to this node will have to flow only through the feedback resistor. So, now what is the voltage at the output? The voltage at the output is the voltage that you measure by using a voltmeter between the output point and the ground, but the output point and this point is also equal because this point is a virtual ground. So, if you measure by a voltmeter from this point to the ground, it is the same as measuring this point with reference to this point. Therefore, the voltage here is nothing but the I flowing through RF, that I is the I in flowing through RF, which is a feedback resistor. So, that is the voltage that you will get here, and it is negative. Why is it negative? Because current is going from this end to the other end. So, whenever its current is entering a point, that point should be negative. Whenever current leaves a point, that point should be a positive point. So, in this case you find the current is coming towards this end, therefore, this end is lower in potential compared to this potential, and this is 0, therefore, this has to be minus. So, output therefore is given as V output is equal to minus I in into RF in this case, where RF is the feedback resistor. The output voltage is equal to minus I in into R2 or RF as the case may be in this case, and this becomes much easier to understand because of the application of the concept of the virtual ground. Now, what happens to the closed loop input output impedances? That we have already seen. The effect of the feedback is to reduce the output impedance and is also to reduce the input impedance. So, Z in with the closed loop, CL means closed loop, Z in with the closed loop configuration is given by R2 divided by 1 plus AOL. The beta is 1 here, 1 plus A beta is a factor loop gain, beta is 1, therefore it is 1 plus AOL, and because AOL is very large, R2 by AOL is going to be very small. So the input resistance is going to be very small, much smaller than R2. Similarly, the output resistance with closed loop configuration is R output without feedback divided by 1 plus AOL. Again, this is going to be a very small value at the output also. So both the input and output impedances will be reduced to a very low value by this feedback. Now let us take an example. What is the output voltage if the input frequency is 1 kilohertz? So even though we have not discussed that the input can be an AC, you can realize because it is an amplifier, it should have a finite bandwidth, and therefore you can apply not necessarily DC current but AC currents also. So what is the output voltage if the frequency of the input is 1 kilohertz? You are applying 1 milliampere peak to peak sinusoidal current value, and that is connected here. What happens to the voltage? The input current of 1 milliampere peak to peak flowing through the 5 kilo ohm resistor. So we can apply simple Ohm's law. V output is equal to minus I in into R2. In this case, I in 1 milliampere peak to peak multiplied by 5 kilo ohm, and that gives to you 5 millivolt. The kilo and milli will go away, so you will be left with minus 5 volts peak to peak. So this current voltage converter will convert 1 milliampere peak to peak current to a 5 volts peak to peak voltage, but again there will be a inversion. The negative sign shows inversion. If the current is increasing, this voltage will be decreasing, and if the current is decreasing, this voltage will be increasing. So you get a 1 kilohertz output wave. Having seen that, now let us quickly see a simulation of the circuit. You can see on the screen a breadboard. You have a dual power supply here, plus minus and ground with 15 volts. You have also a current source, and on this side you have a digital voltmeter. Now we have to wire the circuit. You have the gate, you have the op amp and resistors and all that. So now let us arrange for the building of the circuit. So the IC is put there, the resistor is put there, and the different wiring are done corresponding to the circuit, and the circuit is shown here. It is a very simple circuit, 2 inputs and 1 feedback resistor between the output and the input, that is all. So that pin number 2 is connected to pin number 6, that is a feedback loop, and the value of the resistor is 10 kilo ohms typically in this case. So you have the voltmeter here, you have the dual supply, all the things. Now we will go and switch on the dual power supply, the current source, and the voltmeter. Now I can select either milliamperes or microamperes. So let me select microamperes, and I can increase the current. For example, input is 100 microampere DC, let us say. Then this 100 microamperes going through 10 kilo ohm will give me 1000 millivolt or 1 volt, and that is what you see here. This is 1 volt because it is multiplied by 10 kilo ohm resistor, 100 microampere. Now if I increase the value to 200 microampere, it becomes output becomes 2 volts, you can see that. So I can apply different currents and see the output each case. So this becomes a very simple current to voltage converter. Now what is the use of such current to voltage converter? The applications of these current to voltage converters are many. I have taken 2 typical examples which I would like to show it to you also later on. Here what I have done is the same circuit, the current to voltage converter basic circuit, but instead of the feedback resistor R2, I have put an LDR, light dependent resistor. So if I give a constant current I in now and vary the light intensity here falling on the LDR, you would find due to the light intensity the resistance changes because it is a photoconductive cell, light dependent resistor, and you would find when the resistance changes the output voltage changes, because the relationship is V output is equal to minus I in into R LDR. So you here R LDR is the one which is proportional to the intensity of light falling on that, then therefore V output is equal to minus I in into R LDR can be used to measure the intensity of light falling on the LDR. So it becomes a lux meter to find out the light intensity. There is another way in which the same circuit can be designed. For that what we do is we use the LDR in the current source path. That means you apply a voltage, usually LDRs have got very high resistance in darkness and very low resistance when it is fully bright. So when it is a large resistance along with a large voltage source, you will get an ideal current source, reasonably close to an ideal current source. So we can try to apply a voltage to an LDR in dark, so that the resistance is high, voltage can be anything, and you this because of the large resistance of the LDR you get a almost good current source. So that is what exploited here. So the current I in is now modulated according to the intensity of light falling on it. If the intensity is very high, the resistance of the LDR will become very small and the current will increase. If you make the LDR keep it in dark, then resistance is more, therefore current will become less and output voltage will also become less. So this is easy to understand. I hope these two model. And now there is also another circuit which you can build, same corresponding to the current voltage converter, and that is to use a photodiode. You can use a photodiode amplifier, connect a photodiode at the input stage. Photodiode basically is a current source. When light intensity comes, some electrons are excited to the conduction band. So you would find this becomes closer to a current source, and therefore when I use a photodiode I should try to use a current to voltage converter rather than a simple voltage amplifier. So this is an essential point. So depending upon what you want to convert from one stage at the input stage to the output stage, you must choose proper amplifier, whether it is a trans conductance amplifier, trans resistance amplifier, voltage amplifier or current amplifier. So in this case light intensity is proportional to photocurrent, and therefore that should be proportional to V output. So it is a very simple circuit application of operational amplifier as a current to voltage converter. There is also a fourth application which I would like to indicate to you, and that is to construct an electronic ohm meter. An ohm meter measures the resistance. So we will try to measure the unknown resistance using this circuit of current to voltage converter. If I have an unknown resistance, all that I have to do is wire the current to voltage converter and replace the feedback resistor with the R unknown, the resistance given whose value of resistance is to be formed. So you put the unknown resistance in the feedback loop and give your input current and measure the output. The R unknown you can see is minus V output divided by I input. And if I take a typical example of 1 milliampere current, V output by 1 milliampere is the unknown resistance, and if I take the corresponding value for the milliamps, when it comes to the numerator, when you will get kilo ohms. Therefore the magnitude of the output voltage itself expressed in kilo ohms gives you the value of the unknown resistor. So this is one of the simple examples of application of current to voltage converter. Now I will quickly go to the work table and show you these three examples, and we will perform the experiment and get the result. What we have on the table is the familiar dual supply. I am sure all of you are now familiar with this. We have already seen the earlier experiments. You have the breadboard. In the breadboard there is an op amp and there is one feedback resistor. The wiring is done and the output voltage is measured using this digital voltmeter you find here. This digital voltmeter, which is selected for the voltage range, DC voltage, will measure output voltage. Now the circuit of whatever that we have wired on the breadboard is shown on the diagram above. Just to recapitulate, it is just a simple you have a current source here, you connect a feedback resistor of 10 kilo ohms and you measure the output voltage using a digital voltmeter. This is the same circuit which is wired here, and what I have here is a current source. It is a commercial current source, but one can also do with simple circuits in the lab to generate constant currents, and this is capable of producing currents through very large ranges starting from nanoamperes to several hundred milliamperes by using the dials. Now right now I have kept it in standby mode. So the current, this circuit current source is connected to the input, and that current flows into the pin number 2 of the amplifier, and the output is monitored here. To measure the current, I have introduced a current meter, another multimeter. I have selected 200 microampere range here, and therefore what it measures is the input current. This comes in series with the current source, and then it is applied to pin number 2. This black wire is connected to the pin number 2. So this is actually connected, these two are connected in series at the input. This is the current source, this is the current meter which is measuring the magnitude of the current, and the voltage is measured using the output voltmeter. Now let us try to apply the current. So I do not know whether you are able to see the dial. It is 2 here, it is 0 here, and this is the dot decimal, and therefore 20 point, that is microamperes. So it is 20 microamperes, and that is the current, and you can see here it is in 200 microamperes range and it reads 20 microamperes. 20 is the reading here. So this and this are perfectly matching. You are applying 20 microamperes and you are also reading 20 microamperes in the multimeter, and that is being applied here. You have a 10k resistor, so multiply 20 microampere by 10k, that will be 200 millivolts. The k and the micro will make it milli. So 200 millivolts should be the value of the voltage. I am sure you are able to see here the voltmeter reading is, how much is it? I have to switch on the dual supply, okay, and if you observe the multimeter, it reads 206 millivolts. So this is a very neat presentation. You can see that. Now what I am going to do is I am going to increase the current from 20, let me increase to 30 microamperes. So you can see this current meter reads 29.9, which is 30 microamperes, close to that, and correspondingly if you now observe what is the output voltage, it will be very close to 300 millivolts. So now I keep moving to another voltage current 40 microamperes, 39.8 is the reading here. You multiply by 10k, you get there, it is about 406 millivolts or so. So you can see this current is converted into voltage. Now if I change the range, for example I will bring this to 0 and have 1 or 2 microampere. For example I have kept 2 microamperes here. 2 microamperes multiplied by 10k should give me 20 millivolts. So what you get on the millivolts range is about 21.4. There is a slight variation, it is not perfectly 20 because this 10k resistor is what I read from the color code, but the actual resistance can be slightly different from 10k, maybe 9 point something or 11 point. There is a 10% tolerance, and therefore it can be slightly different from 10k. So if I want to change the conversion factor, the conversion factor is basically the 10 kilo ohm, that is a trans resistance amplifier. So if I change it to 100 kilo ohm here, immediately you will find the same current will be multiplied by 100k and you will get the corresponding output voltage here. So you can increase or decrease this resistance here and get a voltage proportionally at the output. Therefore, it is a very simple and useful circuit, especially when you have for number of different sensors. I also told you that we will show you a simple application circuit using LDR. So now you can see the two circuits which I already showed you on the computer screen. There is one current to voltage converter where the feedback resistor is now replaced by a light dependent resistor LDR. The corresponding circuit is here. You can see the op amp, you see that the LDR here, and that is in the feedback network, and the current source is still here, and current meter is also here, and the output is monitored by the voltmeter here. So everything is same except that in the feedback instead of the normal resistor I have replaced by a light dependent resistor. Now let me apply the current. The current here is about 10 microamperes as read from the multimeter here. It is 10 microamperes, and here also it is 10 point, and so 10 microamperes. And now please observe what is the output voltage you are getting. You are getting something around 33.4 millivolts or so, so around 33 or so. Now this is corresponding to the current that is generated due to the LDR present here. Now if I close the LDR using a small cardboard, you know the resistance will increase, and therefore the current to voltage converter output also will increase, because R increases, I into R should also increase. Now keep observing the multimeter reading as I bring the cardboard and hide the LDR. Now I have closed the LDR, you can see the voltage is somewhere around 180 or so. So when I remove it, again it comes to around 30 or something. So when I close it completely, you find it can go to very high values, 200, 300 millivolts and things like that. That is because when the light is stopped from the LDR, the resistance of the LDR increases, we all know that. So you can see this can be used to detect light intensity. When I close the LDR, the resistance increases, the output voltage increases. When I remove the lid, then the LDR is exposed to a lot of light, and therefore resistance is small and the voltage is also small. There is also another way to get the circuit, and that is, instead of putting it in the feedback, I am using the LDR itself as a current source. So that circuit is shown in the next part of the breadboard. You see another circuit here. You have the LDR now connected to some 5 volts supply. So the 5 volt supply with the LDR becomes a current source in effect, and that is connected at the input, and I put a fixed resistor of about 10 kilo ohm in the feedback here, that you can see. This is the op amp, this is the 10 kilo ohm resistor, this LDR is here, and the one end of the LDR is connected to the op amp, the other end is connected to plus 5 volts, and therefore it is energized with 5 volts. So now I will quickly change the multimeter from here to the next circuit. So now you can see I have connected the multimeter to the second circuit at the output of the second circuit, pin number 6 of the second op amp, and therefore you can see the current now is due to this LDR. The current source is due to this LDR, which is now exposed to a lot of light, and therefore the resistance is very small. You have large current, and therefore the voltage here is around 0.538 or so volts. It is in volts. Now if I cover the LDR, the resistance will increase, therefore the current will start decreasing because it is forming part of the current source. When I close that, current will decrease, and therefore you would find the output voltage comes to millivolts, 147 or something, 135, etc. So if I remove it, it again comes to 0.5 volts or so, and when I close it, it comes to few 100 millivolts or so. So you can see this also can be used as an optical detector for detecting light intensity. This LDR can be used by making use of the simple current to voltage converter. We will move on to the next feedback configuration. You see on the screen, you can see that here the output is connected in series with the feedback network, and therefore it is sensing the current output. It is sensing the current here, and it is also giving as a voltage here in series at the input. So the effect of connecting something in series at the output is to increase the total resistance. Now it is R0 plus RF0, and therefore the effect is to increase the output resistance from this side, and the effect of giving a voltage in series with the input is basically again to increase the input resistance. So the input resistance is also increased, the output resistance is also increased by this configuration, this feedback. So what is the effect of that? Because the output impedance is increasing, then this becomes a current source. It is not a voltage source, because only for a current source the output impedance is very, very large. Usually for an ideal current source it is infinity. And at the input resistance is increasing, that means input will have to be a voltage. So you have a voltage at the input with a large input resistance for the effective amplifier, and you have a large output impedance corresponding to a current drive at the output, and therefore it becomes a voltage to current converter. Input voltage will be converted into a current by this feedback arrangement, or it also can be called as a voltage controlled current source, VCIS. And now let us try to look at the circuit based on this. So what you see on the screen is a very simple op amp voltage to current converter. So in the feedback, this is a negative feedback. You can see that you have a R1 and an R2. So whatever current that is flowing through R2, that and R1, a potential divider, and this voltage is applied here in series with the input voltage, and therefore this is exactly same as what we discussed a moment ago. Now what about the input output relationship? If you want to understand this in a very simple way, you can always understand, because you are giving the input voltage here, this is V in, and this voltage cannot be different from V in by more than what, plus or minus 150 microvolt, we have already said, at any instant, and therefore this voltage will also have to be V in at this point. So if this is V in, this current through that will have to be V in by R1, voltage divided by resistance is current by Ohm's law. So V in by R1 is the current, and that will have to be the same current which is flowing also from the output of the op amp, because there is no current which is flowing in this direction, all the current will have to flow through this, and therefore the relationship is I output is equal to V in divided by R1. So that is the very simple relationship between the, so I output is equal to V in divided by R1 is the corresponding thing, and the input output relationship is output by V in is equal to 1 by R1, as you can see from this equation, and 1 by R1 is nothing but a conductance, inverse of resistance is conductance, and therefore I output is equal to Gm into V in, where Gm is the transconductance, and therefore this amplifier is also called transconductance amplifier, and in this case Gm is actually 1 by R1. The exact equation I output is given by V in by R1 plus R2 divided by AOL, and because AOL is much larger, this term can be ignored, and therefore what you are left with is only V in by R1. So this is also a very simple circuit which will provide you with a conversion from voltage to current. For example, I have a thermocouple. So if I have a thermocouple, it produces a voltage thermo EMF corresponding to the temperature difference between the hot and the cold junction. This voltage I want to measure in terms of a current, so that I can have a thermometer, electronic thermometer. So all that I have to do is connect a voltage to current converter and connect a simple current meter, a milliampere or microampere meter as the case may be, and when you put the two junctions in two different temperatures, that will produce a thermo EMF. That thermo EMF will be converted into a corresponding current by a proper choice of my R1, and therefore you get an output current which is proportional to temperature. Therefore I can calibrate the current in terms of temperature, and then it becomes a very simple inexpensive electronic thermometer. I have given an example here. if R1 is equal to 1 kilo ohm, an output voltage of an input voltage of 1 volt will produce a current of 1 volt by 1 kilo ohm, V in by R is 1 kilo ohm. So that is equal to 1 milliampere. So you get a 1 milliampere current at the output, and if I have 100 ohms instead of 1k, the output current will be 10 times more, it will be 10 times 1 milliampere or 10 milliampere. And correspondingly in all the cases, you know that the input resistance of the closed loop will be 1 plus AOL times Ri, it increases the input resistance. So it will by a factor which is 1 plus A beta, and the beta here is also 1, so 1 plus AOL into Rin, Z output is also 1 plus AOL into R1, both the input and output resistance are increased here, and therefore that is why it is a voltage to current converter or the transconductance amplifier. So I have got here a small example. What is the output current in the figure? You have used an op amp LM12 plus or minus 15 volts. I apply 2 volts RMS voltage at the input, and I have 2 ohms and 1 ohm in series here, and so what is the load power, and what happens if the load resistance changes to 4 ohms from 2 ohms to 4 ohms. In principle it should not matter because the current is decided by only the 1 ohm. So we will try to see that. So 2 volts divided by 1 ohm is equal to 2 amperes, so that is the current output. 2 amperes will flow through the load resistance 2 ohm, producing a load power of 2 ampere high square or 2 ampere whole square into 2 ohms, that is equal to 8 watt. So this is the power dissipation of that particular load resistor. If I make it into 4 ohms, the current still will be 2 amperes because the current is decided only by the 1 ohm resistor, and multiplied by 4 ohm gives me 16 watts. So the output power is increased because the value of the resistance is doubled, the output power is also doubled. So as long as the op amp does not saturate, we can change the load resistance to any value and stabilize with a stabilized current of 2 amperes. So this circuit is also very useful in number of applications. I will show you a simulation of the circuit here on the screen. You have a voltage source, you have a dual supply and multimeter, and this is a circuit. Instead of the load, I connect the voltmeter itself as the load. Now let me do auto setup. So all the ICs are going there and the corresponding wiring pattern is coming out. The dual supply is connected. Now the voltage source is connected to the input, and then the multimeter will be connected. Right, once it is done, let us switch on the power supply, all those things, multimeter, and I give some millivolts. So when I give about 100 millivolt, this resistance is about 10 kilo ohms. So 100 by 10 kilo ohm should give me about 10 volts or something like that. So you would find the reading is corresponding to that, and I can increase the voltage here, and correspondingly the output also changes in a linear fashion. The conversion factor is the 10 kilo ohm resistor that is coming into that. So V in by 10 kilo ohm should be the current that I am getting at the output. Now I will quickly go to the table and show you the demonstration of this voltage to current converter circuit. Here you have the voltage to current converter, the same circuit is shown here, and you can see the op amp here, and I have connected 1 kilo ohm resistor, and this is the current meter which is connected here, and the voltmeter is here. This is the voltage source, DC voltage source, which is connected at the input, and this voltmeter measures in parallel what is the voltage I connect here, and this load is actually the current meter which is connected here. Now if you observe here in the voltage source, I have kept at 100 millivolts, as you can see from the reading on this multimeter, it shows 100 millivolts here, and 100 millivolts divided by 1 kilo ohm gives me 0.1 milliampere, 100. So this is 0.1 milliampere, 100 microampere. So 100 millivolt divided by 1 kilo ohm gives me 100 microvolts, or 0.1 milliampere. So that is what this meter reads. If I increase the input voltage to 200 millivolt, this is reading 200 millivolt here approximately, and you can see it is now 200 microampere or 0.2 milliampere at the output stage. Now if I increase to 300 millivolts, this multimeter again reads 300 millivolts and the corresponding output current is 0.3 milliamperes or 300 microamperes. So corresponding to every voltage here, the corresponding current is obtained by the feedback network that you have here, and the circuit is converting this voltage into a corresponding current. So this is a voltage to current converter circuit. Now there are several applications that one can think of for such a circuit, which is basically a voltage to current converter. The circuit provides very large input impedance and it has got larger output impedance that makes it a current output. So here what I have done is, can we build a good electronic voltmeter which is not very expensive by making use of a single op amp and a current meter, 0 to 100 microampere full scale current meter. So if I have a 0 to 100 microamp full scale current meter, I connect it in the circuit. Then if I connect for example 10 ohms, so 100 microamperes into 10 ohms give me 1000 micro ohms or 1 millivolt. So if I apply 1 millivolt here, it will correspond to 10 ohms and 1000 micro volts or 1 millivolt. So when I give 1 millivolt here, that will correspond to 1 by 10 current, which is 0.1 milliamps, which is equal to 100 microampere full scale. So this becomes a 1 millivolt meter. This 100 microampere voltmeter, current meter is now converted into a voltmeter along with the op amp. So it becomes 0 to 1 millivolt range, it will show a current from 0 to 100 microamperes. Now if I switch the resistor from 10 ohms to 100 ohms, then it becomes, for 10 millivolts you will get 100 microamps. So this, when I switch this to 100 ohms, then this becomes a 0 to 10 millivolt voltmeter. It can measure 0 to 10 millivolt, correspondingly a current of 0 to 100 microampere. So if I now remove the dial of the 100 microampere meter and put it in terms of volts, this becomes a typical electronic voltmeter. So corresponding like that, I can change the value of resistors every decade. For example 1 kilo ohm, 10 kilo ohm, 100 kilo ohm, correspondingly I can go for 100 millivolt, 1 volt, 10 volt, up to 10 volt I can go. So this becomes a multi-range electronic voltmeter. It is a very good electronic voltmeter because the input impedance is very high and the output impedance is also very high in this feedback network, and therefore I just connect a normal current meter, panel meter, which are not very expensive, and op amps are also not very expensive. You can combine them with a few resistors and build your own very high resistance electronic voltmeter. You may be wondering what will happen to the dual supply. This dual supply can be very easily obtained by using two 9 volts batteries. Connect them in the series and keep the center tap to the ground, therefore you get a dual supply +9 and -9, and you can use this, and because the current involved are 100 microamperes, you would find this battery will come for a long time, maybe a few months, several months, and you will have no problem, and it can be put in a very small compact box. Your PCB, your two batteries connected as a dual power supply, everything can be enclosed behind that panel meter, and just take the two leads which are corresponding to the input leads, and that can become a very good voltmeter, electronic voltmeter. You can have a small band switch connected corresponding to these resistors, so that by switching the resistor you can switch the range of the electronic voltmeter from 0 to 1 millivolt, 0 to 10 millivolt, or 0 to 100 millivolt up to 0 to 10 volts. All will give full scale of 0 to 100 microamperes, and you can construct a very nice electronic voltmeter. So there are several such applications that we can think of for these type of circuits. So what today we have seen is that the two different type of feedbacks configuration will give two different circuits. One will be a current to voltage converter and the other is the voltage to current converter, and both of them can be used for several simple applications in normal electronic field. So, next time we will see the next feedback configurations which will lead on to a current amplifier, and then we will go further. Thank you.